Okay, so as mentioned earlier, I'm Cameron. I'm from UC San Diego, and today I'm going to be talking to you about the extent to which distributional semantics can account for affordances. And this was work I did with my lab mates at the Language and Cognition Lab at UC San Diego. So how do we understand the meaning of linguistic expressions? An old answer to this question, which has gained recent popularity, is that words mean what they do because of how they're distributed in language. So for instance, we might learn that the words helicopter and drone mean similar things because they tend to be used in similar linguistic contexts. And although this is a really conceptually simple idea, computational operationalizations of this idea have turned out to excel at predicting human responses to language, and have led some researchers to argue that this is a plausible model of human language comprehension. A potential problem for this account is that representations in these models are not grounded in the world. So elaborating on Searle's Chinese room thought experiment, Harnad invites us to imagine that we are trying to learn Mandarin from a Mandarin dictionary. And although we might be able to learn a lot about how the foreign symbols relate to one another, we have no hope of learning about how those symbols relate to the world around us. And this is exactly the situation that the distributional learner finds themselves in. And it's a problem if we want to use words to do things in the world. An alternative approach starts from the assumption that language evolved in order to coordinate effective action. And therefore, the meaning of an expression will be contingent on the goals of the agent, as well as their experience, and the set of actions that's made possible to them by the environment, or the affordances of the environment. So for instance, the expression "he sat on the chair" will mean totally different things depending on whether he refers to a person, or a mouse, or an elephant. And so to understand language, you need to be able to understand the affordances of the described agents and environments. Embodied theories of language comprehension provide a potential explanation for how comprehenders ground language and compute affordances dynamically. On embodied accounts, we understand language by simulating embodied experiences related to the content of the utterance. So for instance, on hearing "he sat on the chair," you might recruit the same neural resources that you would use to process experiences of seeing, touching, and sitting on chairs. Comprehenders can constructively mesh these activated experiences to simulate experiences that they have never actually experienced directly. It's not clear that a distributional learner would have the same ability to reason about affordances. So chairs have many affordances which might not be obvious from the context in which the word chair tends to be used. So you can stand on a chair, or you can use a chair to fend off a dog. But on the other hand, distributional learners might indirectly be able to learn these affordances. For example, by picking up on the fact that things that you can sit on tend to be hard, and that hard things tend to be good weapons. So this invites the question of whether distributional information is actually sufficient to capture the influence of affordances on human language comprehenders. And if it is, then it would undermine this claim that embodied simulation is necessary. So this is not a new question. In a seminal study, Glenberg and Robertson tested whether human comprehenders were sensitive to the difference between sentences describing afforded and non-afforded actions when the sentences were designed to be equally likely on the basis of distributional information. They presented participants with these passages that were describe a character using an object to solve some kind of problem. So for instance, after wading barefoot into the lake, Eric needed something to get dry. He used his blank to dry his feet. Now, in one version of the passage, the character uses an object which is unrelated to the context, but does afford the intended use. So it's easy to imagine how you could use a shirt to dry your feet. In a second condition, the object was equally unrelated to the context, but didn't afford the intended use. So it's harder to imagine how you could use a pair of glasses to dry your feet. And in a final kind of sanity check control condition, the object was related to the context. So towels, obviously very related to the activity of drying. So participants rated each version of 18 of these scenarios on how sensible they were on a scale of total nonsense to completely sensible, and on how easy they were to envision on a scale of impossible to imagine to easy to imagine. Now, the authors also analysed their stimuli using latent semantic analysis, which is a computational technique that learns to represent words based on the context in which they appear. So they measured the cosine distance between the mean representation of the setting sentence and the critical sentence, as well as between the model's representation of the distinguishing word, which is this object which varies between condition, and the central word, which was intended to conceptually capture the use to which the object was being put, here is dry. So when they were designing the stimuli, they ensured that there was no difference in the LSA similarity measures between the afforded and non-afforded conditions. But there was, in the related condition, the distinguishing object was more similar to the central word. So crucially, LSA can't distinguish between the afforded and non-afforded conditions. So if human comprehenders are able to distinguish between these conditions, it implies that they're using some kind of information that's not available to the models. So as expected, participants rated the afforded sentences as more sensible and easier to envision than the non-afforded sentences. And moreover, there was no strong correlation between LSA similarity ratings and comprehenders' sensibility judgments for the sentences. So Glenberg and Robertson took these data as evidence that to support the embodied theory, that comprehenders must be drawing on embodied experience to simulate these scenarios to understand that the afforded scenarios are sensible where the non-afforded scenarios are not. There are, however, reasons to revisit this result 22 years later. So first, the claim that distributional information in general is insufficient to account for affordances could be undermined by evidence from any distributional model. So it makes sense to at least test this claim with multiple different models. And secondly, there's been enormous progress in natural language processing over the last 2 decades. Part of this has been, as evidence of this, kind of just even in the last couple of years, we've seen dramatic increases in performance at benchmarks like glue and superglue. And this is partly driven by an increase in computational resources and partly by technological advances like the transformer architecture. Finally, one of the problems that the authors identified with LSA is that it has its representations of words are context invariant. So although the word chair means different things in different contexts, LSA is forced to only have one representation for each word. In contrast, modern neural language models can generate flexible representations of words that change based on the context. So these advances collectively kind of raise the question of whether modern NLMs will have a better handle on affordances than LSA did. So in order to address this question, we reanalyzed Glenberg and Robertson's stimuli using 3 modern NLMs, or neural language models. So these are neural networks with billions of parameters that learn from corpora of hundreds of billions of words to predict missing words in a sequence based on the surrounding linguistic context. So we use GPT-3, which is a unidirectional model, meaning that its output is conditioned only on the preceding context, and 2 bidirectional language models, BERT and Roberta, whose output is conditioned on both the preceding and the following context. We listed 4 different measures from these models, or 4 different types of measures. So the first is the most similar to the measure in the original study. So we found the cosine distance between BERT's representation of the setting and critical sentences and between its representation of the central and distinguishing words. Next, we used BERT's next sentence prediction capability to find the probability of the critical sentence following the setting sentence in each condition. Third, we used masking to find the surprisal of the distinguishing word tokens in each condition. So we would essentially mask the distinguishing word from the input sentence and ask BERT and Roberta to predict or to find the probability of each of the distinguishing words in that gap. And finally, we used GPT-3 to find the unidirectional surprisal of each of the distinguishing words following the preceding context. We separately tested whether the condition variable explained variance in each of the NLM measures for the afforded versus non-afforded comparison and for the afforded versus related comparison separately. So here we can see the results of the NLM measures for each condition. So as a reminder, the key distinction is between the non-afforded in red and the afforded in blue. And this was the distinction which there was no difference or no effect of on LSA. Whereas there was an effect of LSA between afforded and related conditions. So the cosine distance between BERT's representation of the setting and critical sentences showed no significant effects of any of the condition differences. The cosine distance between the central and distinguishing words for BERT showed the same pattern of results as LSA. So there's a distinction between afforded versus related, but no effect of afforded versus non-afforded. The next sentence prediction probabilities showed no effect of either condition comparison. BERT's appraisal showed a trend in the kind of expected direction, where you've got non-afforded scenarios are the kind of most surprising or the least likely. Afforded scenarios are intermediate, and related scenarios are the most likely. But none of these differences were significant. And Roberta's appraisal showed kind of the same pattern of results as LSA, with no difference between afforded and non-afforded conditions. In contrast, GPT-3 showed a strong sensitivity to the afforded, non-afforded distinction. Non-afforded scenarios exhibited significantly higher surprisal than afforded or related scenarios. So this result implies that GPT-3 has implicitly acquired the tacit knowledge required to know that shirts are more appropriate for drying your feet than glasses are. And this contrasts with Glenberg and Robertson's initial finding, and it suggests that sufficiently powerful distributional models could be able to learn knowledge that has previously been claimed to result from embodied experience. However, we wanted to test a stronger claim, that is that distributional information can actually account for the influence of affordances on human language comprehenders. So this stronger claim predicts that there should be no residual effect of the affordedness condition distinction after we've already controlled for all of the variants that can be explained by distributional likelihood. So in order to address this question, we gathered more human data from 140 participants using a kind of modified version of Glenberg and Robertson's initial study. So each participant only saw one version of the passage to prevent them from comparing between conditions directly. And we only gathered sensibility judgments, as we thought that asking participants to envision the scenario might kind of encourage them to artificially simulate the situation. We used a kind of nested model comparison to find whether there was a residual effect of condition after controlling for the distributional likelihood of the NLM measure. So essentially we asked whether a model that includes condition explains more variance, or significantly more variance than a baseline model, which is predicting human sensibility judgments on the basis of GPT-3 surprisal. So we replicated Glenberg and Robertson's initial finding that humans show this distinction between afforded and non-afforded scenarios. On the right here, you can see the GPT-3 surprisal, which is inverted to kind of facilitate comparison. And you can see, although there is a difference in the same direction between non-afforded and afforded, the difference is much smaller. And as a result, even when we control for the variance in human sensibility judgments that can be explained by distributional information, there's still a big residual effect of condition of affordedness. So on the left here, you can see the raw human judgment data from the previous slide. And on the right, these are the residuals from a regression model, which is trying to predict human sensibility judgments on the basis of the GPT-3 surprisal. And you can see it's consistently overestimating the sensibility of non-afforded scenarios and underestimating the sensibility of afforded scenarios. Another way of thinking about this is to look at the proportion of variance that's explained by each of the predictors. So a variety of the NLM measures did a pretty poor job at predicting human sensibility judgments, explaining like less than 5% of the variance. GPT-3 performed the best, but it's still only explaining around 13% of variance in human sensibility judgments. Condition alone, by comparison, so this distinction between whether a scenario is afforded or non-afforded, is explaining around 33% of the variance. So it's like there's this 20% gap in variance explained, which is kind of the information that humans have access to or are using to assess these sentences that the models don't have access to. So overall, we found that one NLM, GPT-3, was sensitive to affordances, and this contrasted with Glenberg and Robertson's LSA result, as well as the results from all of our other NLMs. And this raises the question of what kind of linguistic patterns GPT-3 is actually exploiting in order to be able to detect these distinctions in affordances. And secondly, if GPT-3 is only performing better because it's so much larger than the other models, it has around 10 times as many parameters, and this starts to raise questions about, as models get larger and they start to have or to learn from more data than maybe a human will be exposed to in its lifetime, the extent to which these continue to be psychologically plausible models or useful baselines to compare against human performance. On the other hand, GPT-3 was unable to account for the influence of affordances on human comprehenders, implying that humans are using information that's unavailable to the model. However, it's not clear that this is actually embodiment that the models are lacking. There's lots of differences between models and humans, and so we want to kind of directly test this embodiment theory more directly. For example, by asking whether there's a correlation between performance at this task and other non-linguistic tasks which might require simulation, trying to interfere with sensory motor systems to see if that has a negative impact on this task, and also augmenting models with sensory motor or perceptual data to see if that improves their performance at the task. Thanks very much to Ben, Sean, Shauna, James, and Tyler, my co-authors in this paper. Sean is here today as well. Thanks, Sean. And also to Art for providing us with the stimuli and for feedback at various stages of the project. Thanks, everyone, for listening, and let me know if you have any questions.
Yeah, thanks for the very cool work and talks. So this is more like a comments rather than kind of questions. So one explanation for the affordance would be the embodiment, but it seems that lots of the, not say all, but lots of the embodiment or affordance problem can be also coded linguistically. For example, like the shirt problem, right? So the shirt and to dry, you can use a shirt to dry your feet. So for that, you can argue that the shirts and towel are made of a similar kind of material, right? And a towel can be used to dry your feet, and therefore shirt can be used. And so this kind of word knowledge is on one level is that this kind of word knowledge might be missed in the traditional distributional model. This is somehow speak to what Andrew has just presented. That is more about the content, but could be less about the form. So that's one level. Another level on top of that is that there's other talks in this conference saying that in the distributional model in general, there's lots of features that actually, or lots of word knowledge are actually encoded somewhere in architecture. It's just maybe in a specific task when people are prompting the model to do things, right? In specific tasks, it is hard to get access to those information that's stored somewhere in the architecture, and that makes the performance less satisfying in different specific tasks. And so, what's your view on these comments?
Yeah, I think two really valuable comments. So the first one, if I understand it, is that distributional information and embodied processes are just two hypotheses for where this information could come from, and there's others, for example, maybe formal propositional knowledge or relational knowledge, which might not be captured by either of these models. And I totally agree with you. I think that we're setting up a kind of simplified comparison here, partly just kind of updating the framing of the Glenberg and Robertson study, but I think establishing that maybe there is still this difference here and that distributional information is insufficient does raise these questions about there's other techniques we could try or other resources we could try to test other than just embodiment, and I think some of the techniques you suggested sound like really promising directions. The second question, as I understand, is that sometimes models can have tacit knowledge and it's difficult to extract that knowledge from the models. I think that problem is definitely more salient for this kind of prompt engineering problem, where you're having the models produce text rather than produce like the probability of a given word. Although, yeah, I mean, I definitely think we have this problem more here than you would for something like a reading time study, because although we're directly getting the probability of a particular token from the model, and we're not kind of having to worry about this sampling problem, we're still kind of assuming some conceptualization of the problem, or we're assuming some analogy between the sensibility judgments of humans and the distributional probability of a word in a particular gap. And I agree that that's potentially problematic, and I think that will continue to be a problem for distributional models. I'm really sorry, it took me such a long time to answer that question that we're going to have to move on, but thank you so much.
Yeah, sorry for comments a little bit long. Yeah.
Cool. No. Okay, thanks very much again.